All right, so hopefully you can all hear me. We're going to go through the exam right now. Let's open that up. All right, first question. Classify the following statement. You suspect there's less traffic on University Boulevard than on East Colonial. So the keyword there is suspect. This would be a hypothesis. So there might be an observation before that, like you notice when you're on University, you get to your destination faster than when you're on East Colonial. Then you come up with this, your hypothesis, and you'd have to set up some sort of experimentation. And after that, maybe develop a theory or something like that. Substance that can't be chemically broken down into simpler substances is an element. A compound could, it's made up of multiple different atoms, so you could break that up into their corresponding atoms. Same thing with mixtures, you could separate those, but an element cannot be broken down into a simpler substance. Chemical change, so this would be occurring when methane gas is burned, so we'd react this with O2, we'd get CO2 and H2 out of this, something that is chemically different than what we started with. If we shred paper, it starts as paper and it still ends as paper. When ice melts, it goes from solid water to liquid water, but it's still water. And dissolving anything still remains the same substance. So if you dissolve baking soda or table salt or whatever, you can evaporate away that water. You're still going to have that same substance chemically left over that it was before. Now let's do 30 degrees Fahrenheit into Kelvin. Here we go. All right, so we are at 30 degrees Fahrenheit. So first we're probably going to go 2 degrees Celsius and then to Kelvin. To go 2 degrees Celsius, if we think 32F is the same as 0 degrees C, what we have to do first is subtract 32 and then take that whole thing there and divide it by 1.8. So 30 minus 32 gives us negative 2, and then we divide that by 1.8. We get negative 1.11 degrees C, and to that we would add our 273, and we would get to 272 K. Other versions of this is version A. Other versions may have had 20 degrees Fahrenheit instead, but then you're going to set it up the exact same way. You'll come up with something like 266 in that instance, I think. But otherwise, the way you solve it's going to be identical to that. All right. Next problem, we want the density of an object that has a mass of 149.8 grams and a volume of 12.1 milliliters. Again, depending on the version, you may have had a different volume, but you're going to set this up the same way. So we have density is equal to mass over volume. And in this case, it's in grams per milliliters or oftentimes grams per cubic centimeter. Although cubic centimeters and milliliters are the same. So I'm just going to take the mass that we're given, 149.8. I'm going to set that over 12.1. And we get 12.38 or 12.4 in this instance. I believe the other version might have been something like 8.07. Right. Which of these is the longest length? For me, I converted everything into centimeters, but you wouldn't necessarily have to go that route, lots of different ways. So 2.95 feet times 12 inches in a foot gives us 35.4 inches. And then to convert into centimeters, 2.54 centimeters for every 1 inch. This is 89.92 centimeters. Our other length there was 38 inches, so we can do the same thing pretty quickly. 38 inches times the 2.54 centimeters per 1 inch. That gives us 96.52 centimeters, so that's even longer. 1.05 meters, there's 100 centimeters in a meter. So if I multiply 1.05 by 100, that's going to give us 105 centimeters. And then our last length there, option D, is 86.87. So you can see out of all of those, 105 is the largest number. Answer C is our correct answer. And now we have this calculation to do. We want to report our final answer with the correct number of significant figures. So 965.43 times 3.9111. That's in parentheses, so we're going to carry that part out first. And we get 3,775.893273. All right, we don't want to round yet because we are in the middle of a problem, but we do need to note how many significant figures this has. We did multiplication here, and the rule for multiplication is the least number of significant figures. Well, this one here has 5 significant figures, and that has 5 significant figures, so the least number of significant figures is 5. So technically, the 3775 and then the 0.8 are the significant figures there. After that, the 93273 are not significant. But again, we're in the middle of a problem, so we don't want to round yet. I want to keep all those digits there, even though a lot of them are not significant. So now I take this number right here. We carry out our final operation, which is addition. 9,413.4136. We're going to add that to their value, and we get 13,189.30687. All right. Looking at our rules for addition, we take the least number of significant digits after the decimal. Well, we established that the last significant digit here was the 8, whereas this has 4 digits after the decimal. So the least number of digits after the decimal is 1. So I'm going to start to the left of the decimal, and I'm going to go all the way until I hit that last digit, or that first digit after the decimal. So our final answer with the correct number of significant figures should be 13,189.3. What does X represent in the following following symbol? So this has an atomic mass of 80 and an atomic number of 34. So atomic mass of 80, it's got, what would that be, 46 neutrons. But the thing that makes it what it is are those 34 protons. And if we look on our periodic table, what has 34 protons? These should be the selenium. Yep. So Se, selenium, element 34. All right, we go back to the exam. Which of the following statements is true? Other than hydrogen, nonmetals are located on the right side of the periodic table. That is true. Metals tend to gain electrons. That is not true. Metals tend to lose electrons and take on positive charges. Noble gases are very reactive. No, they are typically unreactive. And then D, most metals are found on the right side of the periodic table. No, it would or should be the A there. All the nonmetals are found typically to the right there. nitrogen, oxygen, sulfur, fluorine, helium, etc. All right, what's the coefficient here? So we want to balance this out now. All right, so we've got aluminum plus oxygen goes to form aluminum oxide. All right, so at the moment I've got one aluminum on the left, two on the right. That's not good. I've got two oxygens on the left and three on the right. So what I want to do here is put a 2 in front of this. Actually, let's change the color again. Okay. If I put a 2 in front of this, it will give me 4 aluminums and 6 oxygens. If I put a 3 in front of the O2, that matches now, 6 oxygens on each side, and then a 4 in front of that, and now the aluminums match. So the one that we were interested in is what's the coefficient in front of the aluminum. That should have been a 4 when this is balanced. All right, next we want to know what's the correct number of protons, neutrons, electrons, etc. for silver. Silver with a +1 charge, and this has an atomic mass of 108. Well, silver is element number 47 on the periodic table, so we have to have 47 protons. It has a +1 charge, so it had to have lost an electron, or it has to have one less electrons than it has protons. So it has to have 46 electrons, and if its mass number is 108, which is the number of neutrons plus protons, then we've got to have 61 neutrons left over to make up the correct atomic mass there. So for version A anyway, the answer would have been C. We have 6.030 times 10 to the 24 molecules of potassium chloride. So we need to find out how many moles of potassium chloride is this, and then multiply that by the molar mass of potassium chloride. So we can take the number of molecules we have here. Let's fix that. And divide that by Avogadro's number. So when I do that, we get 1.00133 moles, or sorry, no, 10. Sorry, should have been. Oh, we get 10.0133 moles of potassium chloride. And then we multiply by the molar mass, which should have been 74.55, I believe. Take the mass of 1 potassium, which is 39.1, plus 1 chloride, which is 35.45, and you'll get to that molar mass. And you get 746.5 grams of potassium chloride. All right, naturally occurring sample has 2 isotopes. First has a mass of 68.9255, and it has an abundance of 60.11%. So we're going to take that isotope, its mass times its abundance, and then we have our second one. Times its abundance, which is 0.3989. And that's going to give us the atomic mass of this element, which should be, let's see, 68.9255 times 0.6011, 41.4311 plus 28.6907, and we get 70.12 in this case. All right, an ionic bond best described, so. All right, so this question was originally a covalent bond, and there was only one correct answer, which would have been A. But now this was ideally actually could have been answer B, C, or D. So I changed what it was and should have gone back and changed some of the answers, but didn't. So really technically B, C, or D would be a correct answer there for 14. Give the appropriate name for this compound. So we've got copper and nitrate. Copper is a transition metal, so it can have different charges. So we have to indicate the charge on that. Since nitrate has a -1 charge and there's two of them, we need a +2 on the copper to balance that. So this would be copper 2 nitrate. And then we have these hydrates or waters at the end. We have to indicate how many. There's 6, so that would be hexa. So we have copper 2 nitrate hexahydrate. The formula for our acid here, we have nitrous acid, which means we need the polyatomic ion nitrite, which is NO2. So nitrous acid would be HNO2. Calculate the mass percent, let's see, of oxygen in the following compound. All right, and we've got N2O5. So our total mass here would be 2 nitrogens, 14 plus 14. And then our 5 oxygens, 5 times 16 should be 80. So the entire mass is 108. And we want to know the mass percent composition of the oxygen, or just the oxygen. So I would take the mass of the part we're interested in, the oxygen, put it over the mass of the whole thing, and that should give us 74.1%. All right, give the correct formula for tetraphosphorus decoxide. So if we have tetra, that's 4. So I need 4 phosphorus, and deca is 10. So we need 10 oxygens. So that's our formula right there. And if a compound has an empirical formula of PCl3, so we have a 1:3 ratio of phosphorus to chloride, and it has a molar mass of 411.96 grams per mole. We want to know what's the actual molecular formula. So what we can do is find out the mass of the empirical formula. What is an empirical unit? And that should be the 3 chlorides. Each one's 35.45. So multiply that by 3. You get 106.35, and then add the phosphorus, the 1 phosphorus to those, and you get, or you have 30.97. That gives you 137.32. So we want to know how many of those empirical units will go into our molar mass. The answer is 3. So we have 3 times that empirical formula, or this here should be our molecular formula, which was answer C on version A. And then lastly, question 20. performing combustion analysis. So we have a compound that only contains carbon and hydrogen. We don't know how many, what the ratio is. We don't know the empirical formula, but we're trying to find that. So again, that's going to combust with oxygen, and we're only going to get CO2 and water, and all the carbon that was in the original sample, come on, is going to be there in the carbon dioxide, and all of the the hydrogen that was in the original sample is going to be there in the water. So we need to find out how many moles of CO2 do we have and how many moles of water do we have. So we'll take our 22.85 grams of CO2, divide that by the molar mass of CO2, and then there's one carbon for every one CO2. So however many moles of CO2 we have, we're going to have the same number of moles of carbon. And that is 0.5192 moles of carbon. Now we have to do the same thing for the hydrogen, specifically the water. That's where the hydrogen is located. So we're going to take the mass of water that's produced, 14.04, divide that by the molar mass of water. And for water, the hydrogens there's 2 hydrogens for every water. So once we find the moles of water, we have to multiply that by 2 to get to moles of hydrogen. That should be 1.5586 moles of hydrogen. So now I have my ratio of carbon to hydrogen. Although it's not a whole number ratio, it may not be really easy to see what that whole number ratio is. So to make life a little bit easier, what I'm going to do is get one of them, at least one of them, into a whole number ratio. So I'm going to divide the carbon by its value, 0.5192. That'll, of course, give me 1. And I'm going to divide the hydrogen by the same thing. And when I do this, we should see it's a 1-to-3 ratio, or that right there is my empirical formula for this one. All right. That does it for all of this. If you have any questions, feel free to ask. If you think your exam was graded incorrectly, there was an error, stop by any of my office hours. I have all the scantrons, so we can look at the scantron. We can figure out, was there an error? Did you just bubble it in, not dark enough, whatever? And if that's obvious, we can fix it. Otherwise, read up on chapter 4, and I'll see you in class on Thursday.